Now we are going to learn about the nitration of benzene. So in this one, here we have benzene ring and we are going to react it with two reagents, two strong reagents. These are strong acids HNO3 and H2SO4. So these are going to put a nitro group on the benzene like this, NO2 group. So this benzene ring with a nitro group attached to it is known as nitrobenzene. And this is an example of electrophilic aromatic substitution because here what was present earlier was hydrogen. It has gone ahead and replaced that hydrogen and substituted that hydrogen with the NO2 group. So this is a electrophilic aromatic substitution. Electrophiles, you already know that these are the, the substances, these are the entities that have positive charge on them, right? Now let's go into the mechanism. So this is your mechanism here. So first we are going to generate the electrophile. So how are we going to do that? So for the mechanism, we have this thing here. This is a HNO3 structure. This is how it looks like. And the with the N we have a double bond O, and then with the one of the oxygen we have this H attached, and this oxygen has 2, 4, and 6 lone pairs and a negative charge on that. This is a formal negative charge. Whenever oxygen has 6 lone pairs, it will have a negative charge. And then here is your sulfuric acid. This is how it looks like. So two hydrogens attached to these O's, and then S double bond over here and S double bond over here. Okay. Now what will happen? We want to knock out this OH group from here. Okay, because we want to generate NO2. Okay, so we don't want this OH group. So what we are going to do is this. Because you already know that oxygen is very electronegative here, and it is attached to the hydrogen. So this shared pair of electron kind of lies. It has more oxygen has more authority on this one. So what will happen? This H bears a formal positive charge. So this is a partial slight positive charge. This is a delta sign and the lowercase delta sign. And what will happen? So as soon as this positive charge is seen by this oxygen, it will this lone pair will go ahead and attack it here and try to knock out this hydrogen from the oxygen, right? So these two will strongly attract each other, and this bond will shift towards the electron pair which is involved in this bond will shift towards the oxygen. Okay, so this is how this step looks like here. So what will happen is they grab the hydrogen, and there are two hydrogens now, right? So this hydrogen will attach here. So I just wrote OH2 here. So there are two hydrogens attached to the oxygen, and since he used his lone pair here, so he will require acquire a positive charge, right? And then what will happen next? Uh, so uh, so for this molecule here, what will happen? So O doesn't like to be positive because he is very electronegative. So as soon as he will have the positive charge, so what will happen? He will try to he will try to have this electron pair from this shared pair of electrons involved in this bond. Okay, and then he will try to leave. So he will grab these electrons that are involved in this bond. Okay, and he will try to leave. So what left? Two hydrogens and one oxygen. So I wrote H2O here. And since nitrogen lost his electron pair, so it will acquire a positive charge here. And what will happen? Nitrogen, this oxygen here with this lone pair will move here and restore the another bond here. So you have NO2 here and with a positive charge here on the nitrogen and this H2O. So nitrogen, this is how we generated our electrophile. This is the electrophile which is going to attack the benzene ring. Now let's go ahead and see what will happen here. So I just drew the benzene ring here, okay, with three double bonds, and then it is going to react with this electrophile here, which is your nitro group, okay, the nitrogen with a positive charge. So what will happen here? So as soon as this double bond here, so nitrogen is also very electronegative. So the electronegative elements, they don't like to be positive, so they are highly unstable. So because this is a very very stable thing, aromaticity, it will not break as such until the environment around it forces it to do so. So to disrupt the aromaticity, you require some strong instability conditions. So this is unstable condition. Nitrogen is a positive charge, so this double bond is supposed to attack here to compensate for this positive charge on the nitrogen ring. And let's see what will happen next. Now what will happen next, let's see. This pi bond is going to attack here, and then let's write the result of that. So this is your benzene ring with two bonds, pi bonds here, and this bond attacked on this one. So here's your two hydrogen bonds, which are here, and then what will happen? This will go ahead and attach here like this. So this N double bond O. So when it will attack here, so this pi bond will break. You can break this one also, doesn't matter. Both are same, and then uh, let's go ahead and write here the other oxygen. Okay. So let's write the electrons here around it. So since this bond break oxygen, this one has three lone pairs of electrons and one negative charge. Okay. And this one has two lone pair of electrons. Okay. And whenever nitrogen is involved with four bonds here, like one here, two here, and one here, it will have a common positive charge. So let's go ahead and write the positive charge here, right? So since this bond break and this nitronium ion independent attached here, so this one has the positive charge here. There is a positive charge here on the benzene ring as well. We don't want to forget this because this bond attacked here, and this nitronium ion attached here, so there is a positive charge here. Now moving on, we are going to now do this is a lone pair of electrons. I'm going to draw it again. It seems like a negative charge. Let me put it here like this. O and these two dots here. Now we are going to react it with a base, which will go ahead and resume the aromaticity of this benzene ring. Okay, let's see how. So we have two options here. We can go ahead and react it with water, because since we generated water here in this reaction, on this the water can act as a base as well, right? You already know that from your prior knowledge. And then also here we generated this base here. I will show you how. So this is HOS. Okay, I'm going to draw it here for you. Let's see what we had after the reaction when this H2SO4 lost the hydrogen. So we have this HO, then S double bond O, okay, and then you have O with the negative charge. Okay, so since he kept the electrons here, right? Now you can go ahead and use this one or use this one. The choice is yours. I will just write here the base because they're acting as base. They both have lone pair of electrons here. This oxygen has a lone pair of electrons. I'll just write B here. You can draw the full also. Let's draw full only like this. It will react with mm, here. So we have S double bond O, double bond O, and you have OH here, and you have O like this. Okay, so it will go ahead and what it will do, because what we learned in the previous electrophilic aromatic substitution. So this benzene ring will like to compensate for the loss of this hydrogen here. Okay, and then restore the aromaticity. I'll show you how, because this will be lost here. This hydrogen will be accepted by this oxygen. This base will see this H, which is very very positive, and what will happen? It will resume this bond here uh, for the benzene ring, and the aromaticity will be restored. So I already told you, because aromaticities make the things extraordinarily stable. Okay, so what will happen? The benzene ring will kick this hydrogen out and restore the aromaticity. So let's go ahead and draw the result of that. So we already had these double bonds here, and since we lost it and this bond moved here, so the aromaticity is involved. This step is highly stable. It makes the ring highly stable, and then what we have is this nitro NO2 group here. Okay. Um, And then we have this H2SO4 here. It will go ahead and grab this oxygen, and so we have HO has double bond O double bond OH. Okay, so you can see here we have generated nitrobenzene. This is an example of electrophilic aromatic substitution. Here earlier there was hydrogen, so nitro group went and replaced that hydrogen. Okay,